Hello everyone, welcome to AI Research by Lithuanians in 2022 meetup. My name is Deividas Matačiūnas. I am board member of AI Association of Lithuania, and today is my one of the favorite meetups of the year because once a year we have AI Awards, and in this meetup we presenting nominees for 4 categories. So these categories are Best Research Paper, AI Company of the Year, AI Application, and AI Publicity. So I want to present all the categories and all the nominees. So let's start from Best Research Paper. So nominees for Best Research Paper of 2022. So the first one is Marius Klimavičius, CEO of Black Swan Technologies. And his paper was presented in workshop on application of computer vision, one of the prestigious workshops in computer vision space. And the Black Swan is one of the fastest growing AI Lithuania AI company. And his paper called Occlusion Robust Object Post-Estimation with Holistic Representation. So if you want to read this paper, there's our link below the image. And one thing I really want to congratulate Marius because he is one of the leaders in AI field and computer vision, and also very glad that we have AI companies that are writing paper and publishing in prestigious workshops and conferences. The second nominee is Mantas Mažeika, PhD student from University of Illinois. His paper, How to Steer Your Adversary Target an Efficient Model Stealing Defenses with Gradient Redirections, was published and in ICML, International Conference of Machine Learning. So this is one of the famous machine learning conferences, one prestigious one. One thing about Mantas, he's probably most productive researcher because I see 2 publications in NeurIPS this year, 1 panel in NeurIPS this year, and 1 competition. He also have 2 papers in ICML, which is like incredible to publish, and so many papers, and all these papers are so good quality that they been always accepted in these prestigious conferences. So this is amazing, and this paper is super interesting if you want to read. Also the link below. The third our nominee is Ugne Klibaite, postdoctoral fellow at Harvard University, and her paper was quite different from others and was published in Molecular Autism. And the paper name is Deep Phenotyping Reveals Movement Phenotypes in Mouse Neurodevelopmental Models. So this is super interesting topic, and Ugne prepared 10 minutes presentation about this. So let's watch it.
Hi, I'm Ugne Klibaite. I'm a postdoc at Harvard.
Sorry, technical issues.
Currently, and I'll be telling you about some work I did with my
Sorry, technical issues. One moment, I will show the video.
Hi, I'm Ugne Klibaite. I'm a
Sorry about technical issues, but we can hear
postdoc at Harvard currently, and
right
telling you
now.
about some work I did with my prior group at Princeton, where we are interested in unsupervised behavioral classification, and specifically here we're looking at mouse neurodevelopmental models, so mouse models of autism spectrum disorder in particular. And so the first thing we did is simply made really good reportings. So in order for all of these computer vision techniques to work, you want really clean data. And so we took each of our models and wild types and recorded them for 5 consecutive days in this open field arena for 20 minutes per experiment. So we had lots and lots of hours of behavioral data. And as you can see here, the first step after this data collection process was to get a skeleton representation of the animal for further analysis. So in recent years, there's been a lot of progress made in tracking techniques. So we can take a movie like this and train a convolutional network to predict where body parts are just by giving it many examples of this. So I would label 1,000 frames of a mouse in different postures, and this network would then infer where these joints are on frames that it had never seen before. And so this is an example of an 18-point skeleton that I trained that I used for further analysis. Okay, so from this type of tracking, we can get really, really clear kinematics. So what each body part is doing over time. This is just showing a quick little run. So you can see there's this sort of signal that lets you see that it's locomotion, it's running, right? And if we sort of zoom out a little bit, we can see that this kind of thing happens over and over again, and also other sort of interesting things happen. So this more subtle signal, but still that has these this variation in some joints is actually grooming. And so we can use this to our advantage. And this is where I'll introduce this behavioral embedding pipeline, which is how we categorize all of the behavior in all of these videos. So first we start with those movies, with those labeled positions. And from those, we can construct a distance matrix. So this takes out any rotational or translational invariance. If we like, we can reduce this further with a PCA on this signal. And so at this point in time, what we have is a way to reconstruct just the posture of the animal. We don't know anything about what's going on before or after. And so that's why this wavelet decomposition step is very important. This is where we're looking at how things are changing over time at different frequencies. So you construct this really high dimensional signal that tells you about how the animal is moving. And we use this then, clustering this signal or performing a dimensionality reduction on it and clustering it in a lower dimensional space gives us our behavioral labels that we'll use to classify behavior. And so really the key part of this is that if you're in the same behavior, according to this label, this high dimensional signal will look fairly similar across those different time points. And so what does this look like? Well, we find a variety of behaviors. And so we actually start by clustering into 100 different clusters. And then using just human annotation, we pare this down into things that we find interpretable. So we find things like the mouse sitting still, the mouse grooming, the mouse running. And so all of these sort of have a particular sort of dynamic and postural fingerprint that the algorithm finds and clusters and produces this label. And so here are just many examples from grooming. So that was one example before, and here are sort of 5 different specific clusters of grooming. So if you look really closely, you can find that, well, in some of them, there's more vigor in how the head moves, or there's more movement of the limbs. And so we can really go and do really fine scale annotation and analysis. But for now, I think we're just going to focus on these big 8 categories. And so one thing that we get asked a lot with this kind of pipeline is how well does it agree with human annotation? Because classically, this type of work is done with human annotators watching movies and labeling what the animal is doing. And so we found some human annotators, and we can compare our algorithm, and we find that there are lots of periods, most periods, where humans and the algorithm are in high agreement. And we can explore what happens when they're not. And so we find that overall, our pipeline, which we call mouse motion mapper, is sort of more likely to envelope the entire bout of locomotion, as you can see from the trajectories here, whereas a person might only label it as locomotion if it's like very clearly within a stretch of locomotion. And the other thing about this algorithm is that it's more likely to switch between the classes. So a person might be more likely to call it slow exploration, whereas the algorithm says, well, you were exploring and then you turned and then you explored and then you turned. And so it would independently label all these things. And so whether that's good or bad really depends on the scientific question you're asking. But the strength of this is that we know that by applying this algorithm, you will be consistent. So it is known that human annotators get tired, are not consistent across days or between people. And an algorithm like this, you know that giving it hundreds or thousands of hours of video, given the same skeletal representation and the same temporal representation, it will produce the same exact behavior each time. Okay, so going back a little bit, looking at our different groups, we can see with really basic measures that there are differences between them. So for example, catnaps are sort of known to be more active. They're this kind of model. And we find that if we look at just the distance traveled, so something we don't need fancy tracking for, within the 20 minutes of each experiment, we find that yes, they travel much further. And something else like the speed during locomotion, we know that our cerebellar model just runs more slowly in general. Like this is something that we were expecting from this model and that we see borne out in this kind of data. But our technique allows us to look more closely at each specific bout of locomotion. So each time our algorithm labeled something as locomotion, we can go and extract out the joint traces and really align each step, and then look at something like the properties of how each step happens in that type of animal, in that group of animal. So just by looking visually, we can see that our cerebellar mutant has really uncoordinated locomotion. And when we look at the summary statistics for this, so which paw goes after which paw and what is the phase cycle in order, we find that they are much less coordinated than their littermates who don't have this perturbation. Okay, so that's just locomotion. So, and how we can explore something like that. And so here I just have a few examples of sort of the less coordinated versus the more coordinated running from these clusters, from the original 100 clusters. But I think we want to look at all behavior, and that's something that we can do using our method, even behaviors that people might not look at as important. So these very small bouts of exploration, sniffing. And so we can find across days how behavior changes, how the animal responds to being in the same arena day after day. And we can also look across groups. So what's the difference between males and females? Well, females were less likely to be idling around, but they were more likely to be running, for example. Whereas, one of our models had very few behavioral changes, just a little bit in locomotion. And this other more, I'd say, strong model had a lot of changes over the course. And so this is looking at the summary statistics. So of total time, what behaviors was the animal performing? But we can also look temporally. So over 20 minutes after a mouse put into this arena, what was the likelihood that it was running, right? And that goes down along the first day, whereas the likelihood of grooming increases over time. And by day 4, you see that there's this really clear progression that each day it gets a little bit more likely that you're grooming and less likely that you're performing some of these active behaviors. So this is for the wild type, so just the wild type males. We can construct this sort of time series of what we think habituation looks like. And here's an example just to give an idea of what these animals are doing. On day 1, they're running around. Here's an ethogram of what they were performing over time during this full minute. Whereas by minute 18, so at the end of the recording, they take a lot more breaks, they slow down, they will sit, they will groom. And this is very normal based on based on our analysis. However, when we start to look at these different neurodevelopmental models, we find that they show some differences in this process. So for example, the catnaps, who are the very quick ones, do sort of habituate. They start running a little bit more than their counterparts, but they do habituate across days. And they also just start grooming more. So they actually sort of overdo it, start running less and grooming even more than the wild types. Whereas the TSC1 mutants never actually plateau out like the normal animals do. So they will continue to run and amble around a lot, and they will never start to groom, at least not within the first 4 days. So we would say they are sort of deficient in this ability to habituate, to come into this new environment and get used to it. And so it seems like it might be surprising for them each day that they're put into that arena. And so I just showed a few little tidbits, but in this paper, we really tried to explore lots of aspects of behavior across different time scales. So like I showed the locomotion coordination. I didn't talk about grooming, but from day to day, the behavioral evolution. And so I hope that I've convinced you that this sort of method for quantitative behavioral analysis can really get at a lot of different questions all at once with a fairly simple data set. And with that, I would just like to say that this is part of sort of a larger body of work. So when I started working with Josh Shavitz, I was working with flies in social situations. And then Sam Wong, we did this mouse characterization project. And now a lot of things have changed just in the few years since we were working on this, where we're tracking animals in 3D in social context while we're measuring neural activity. So it's a really exciting, fast-growing field. And thank you so much for listening.
Yeah, thank you so much, Ugne. And we are going back. Yeah, so thank you very much. And one moment. Yeah, very sorry for technical issues. And our second nominee is Justas Dauparas, postdoctoral fellow of University of Washington. And his work was published in Science Journal, one of the prestigious journals in the world. So congratulations, Justas. And his paper is called Robust Deep Learning Based Protein Sequence Design Using ProteinMPNN. So Justas also prepared 10 minutes presentation. So one moment, I just need to, because of technical issue, I just need to share another screen. So one moment.
Hello, everyone. My name is Justas.
Yeah, so we can hear Justas talk right now.
Hello, everyone. My name is Justas Dauparas. I'm a postdoctoral fellow at the Institute for Protein Design at the University of Washington. And today I would like to present my work on protein sequence design using ProteinMPNN. There's been a great progress made on protein structure prediction, which is given a protein sequence, we'd like to determine 3D coordinates of all the atoms using AlphaFold or Rosetta Fold. Today, I'm going to talk about the task, sort of like inverse task. A given protein backbone coordinates, I'd like to design a sequence that folds back into the same structure. So we'd like to have a consistency between what we wanted to design and what came out of the structure prediction methods. So we want to design sequences, probably many sequences that satisfy this constraint. For those who are not familiar with protein structure, we can think about analogies between the image and language domain. So you can think of an image as the protein structure. This protein structure could be represented as a distance 2D grid points. And the sequence is a text. So for example, an image generation would be mapping a text into the image, or for structure prediction, mapping protein sequence into protein structure. And on the other hand, given a protein image, we can train neural networks to do image captioning, and the same for sequence design. Given protein structure, we will train the model to design sequences. So more formally, the problem statement, what we'd like to have is that we would like to have a protein structure as an input, and also we would like to mark parts of the structure, for example, the red parts that we want to redesign, while the rest is fixed. We would like to have multiple chains and also predict uncertainties. The model is going to be trained on the same protein data bank, which are the crystal structures of about 20,000 proteins. So it's the same data set that was used for protein structure prediction. The model is a graph-based neural network that, for example, if we have chain A and chain B in green and red, correspondingly, we can think of the residues as the nodes in the graph, and the edges are the interactions between the residues. The features as an input will make the graph sparse. We assume that the local neighborhood matters. And on the edges, we'll put features that would say how far away these residues are in the primary sequence space, or if they're in the same or different chains. And also, what is the geometry? What are the distances between the backbone atoms? The sparsity assumption can be checked by training models with different number of connections in the graph, starting from 16 all the way to 64. And I'm plotting the accuracy on the validation set for the same model, trained in the same way. We can see that the performance saturates at around 32 nearest neighbors, which means indeed the sparse graph assumption is enough to capture the data. The distances between the atoms are encoded using what's called radial basis functions. We can think of sort of like creating channels or a soft binning for different distances. Interestingly, relative frame orientations, because we could make, or dihedral angles, do not add more. So the distances is the most easy feature for the network to use. The training objective is going to be categorical cross entropy, minimizing categorical cross entropy, which is a classical objective. So given a true distribution that we observe in the data and the distribution that we predict, we'll try to maximize the log probability. So we can sort of step back and think about this task as a node classification task. So given a graph that potentially consists of multiple chains, we'll make these local neighborhood graphs, and using the edge features, we will predict the node features as sort of probabilities, and then doing the inference, we would like to sample from these probabilities. So we'll make the autoregressive assumption. We will factorize the joint probabilities into the conditional probabilities, as is done for language translation too. So the architecture is going to be a message passing neural network. It is encoder decoder setup, very similar to the attention is all you need paper for the language translation. And sort of input language is the protein backbone, which gets transformed in the backbone encoder, and then added to the sequence decoder that is run iteratively, and we sample 1 amino acid at a time and run multiple times. Interestingly, the decoding order, to be able to achieve the conditioning on either left or right, we do a random decoding order, so the model learns all different decoding orders. Let's have a look a little bit more closely at the backbone encoder. So the backbone encoder takes the edge features, which are distances, node features, which is zeros, and then updates the nodes using message passing, just summing over the edges, having a feed-forward layer, and then a layer that updates the edges again. And we have 3 layers of these networks. The hidden dimension is 128, so the model is quite small. For the decoder, we just have a very similar architecture, except we're not updating the edges. So we update the nodes with message passing, and then we have a feed-forward layer that predicts our probabilities, and then we sample from this probability distribution with some temperature, and then we condition on the sampled sequence, and we do it again. We use the random decoding order, so during training, the model gets a randomly chosen decoding order that has to learn. The model is quite small, so it's about 1.7 million parameters. We have 3 encoder layers, 3 decoder layers, 128 in the dimension. If you make the model bigger, the model very easily overfits, so the training loss is much lower, but the validation, it's very hard to improve on the validation loss. In comparison, the structure prediction models come in about 100 million parameters. So this task is more local, and it's easier to overfit. So here I'm describing a single chain benchmarking. So we have a baseline model that was previously described in NeurIP 2019 that achieved about 41% sequence recovery on the AlphaFold models, but just adding geometric features, which is the distances between all the atoms. Instead, in this case, in this model, they use the angles. We can achieve an extra 6% improvement in the performance. But furthermore, adding ProteinMPNN MPNN edge updates can also increase a little bit of performance. And interestingly, training on random instead of forward decoding order also leads to a small improvement as opposed to hurting the performance. If we compare our model with a physics-based approach, which is Rosetta, which is often used in practice to design sequences, the model is better across all the different geometric ranges. So this sort of represents how much of the context there is available when predicting the sequence. So we get in the core of the protein, so it's the middle of the protein, there's lots of constraints. We get a really high, almost 90% sequence recovery, whereas on the surface of the protein, so at the very top, there's not much of the constraint what residues to pick. So the model gets about 35% sequence recovery, but it outperforms Rosetta in all the cases. Furthermore, we can check how well predicted negative log probabilities correlate to that true accuracy, and they are correlating quite well, so that we can know when the model is uncertain about a specific prediction that maybe the backbone is of a low quality. The very important point in this paper is that training a model with a backbone noise increases robustness, and it's very important. If we take just the PDB structures and we train without any noise, the model achieves about 55% sequence recovery, but just adding a very small amount of noise, 0.02 angstroms, leads to about 5% decrease in sequence recovery. But this amount of noise is really, really small compared with the errors in the crystal structures, which says that the model is actually picking up on some artifacts that somehow it gives out the sequence. So we don't want to use the model that is overfitting, but what is interesting is that if we add even more noise, the sequence recovery goes down, but this match between the input structure and the output structure using AlphaFold increases. So we, in practice, want to use the model that is actually more robust. It's trained at about 0.2, 0.3 angstrom noise to achieve the maximum input-output consistency. There's some examples using ProteinMPNN, some of the crystal structures that people in the lab designed. There's dimers, trimers, all different structures, and they match quite well, the crystal and the design structures. Furthermore, we can design a large assemblies of thousands of proteins to make these beautiful rings that are here visualized using negative stain electron microscopy. This tool has been also used to make the nanoparticles. So in this case, I'm showing the crystal structure of the tetrahedral nanoparticle. Then these particles are used by adding stabilized antigens to make vaccines. So now I'm going to show a quick demonstration of the tool in the hugging phase. So we're going to redesign this called top 7 protein. It's called 1QYS, and show how quickly this model works. So this is the hugging phase. So we enter the 1QYS and we select, for example, let's run 2 sequences. So press run, and then the model is running. So we have the input sequence and then the 2 design sequences. We can see it's about 44 and 46% similar to the native sequence, and those are uncertainties. And then we can also run AlphaFold to predict these structures. So if I show the predictions of the model about 0.7 angstroms, 0.8 angstroms away from what we expected. And if we look at the PyMol, it's interesting that of course, some of the amino acids do not match, but overall, the backbone matches quite well. So we redesigned the backbone that we wanted to. So to sort of recap, ProteinMPNN is a sequence design method. Given a protein backbone, we're generating sequence in multiple sequences. It's fast and lightweight. It does not require any expert customization. You can do symmetry and negative multi-state design and so on. So I'd like to thank everybody who contributed to this paper and all the team in the IPD. And thank you for listening and inviting me to present the Lithuanian AI Awards. Thank you.
Thank you very much, Justas. Amazing presentation. And just quickly jump to another talk. Yeah, so another nominee, thank you, Justas, thank you, Ugne, amazing AI capabilities, protein structure, mouse behavioral. This is like super interesting and amazing work. Congratulations. The last our nominee is, Karolis Martinkus, PhD student of ETH Zurich. His paper also was published and accepted to prestigious conference, International Conference of Machine Learning. And the paper name is called SPECTRE. Spectral conditioning helps to overcome the expressivity limits of one-shot graphs generators. Quite interesting name, and Karolis also prepare presentations, so just 1 minute and we can show it.
Hello, I'm Karolis, and today.
Okay, so we can right now start to checking Karolis' presentation about SPECTRE paper.
Hello, I'm Karolis, and today I will present our work on spectral conditioning for graph generation, as presented at ISML this year. So first, why graphs? Graphs are a very general data structure that can represent many things. You know, a social graph can Hello, my name is Karolis, and today I will present our work on spectral conditioning for graph generation, as presented at ISML this year. So first, why are we interested in graphs? So anything, almost anything, like a social network or a molecule can be a graph, right? As long as we have some nodes and some well-defined interactions between them that we can represent as edges, we have a graph. And in this work, we aim to generate any sort of graph. So if you have like a data set of molecules, you want to generate more molecules that are somehow similar, right? Or you have a bunch of small social networks and you want more social networks that are similar, right? And in this context of generic graph generation, there are two big problems. One is that while we can represent a graph as an adjacency matrix that of ones and zeros, graph actually doesn't have an ordering of the nodes. So we can permute the rows and columns of this adjacency matrix, and we will still have the same graph, but a different adjacency matrix. And in fact, it's actually very hard to tell that, you know, such two permuted adjacency matrices in fact correspond to the same graph. Another problem is that graphs in the same data set or same distribution can vary largely in size. For example, you know, we can have a molecule with 5 atoms, and we can also have a molecule with 500 atoms. So far, machine learning approaches mostly fell into two paradigms in regards to graph generation. So the first paradigm is autoregression methods, where you first, when generating a graph, start off with just having one node, and then you add one node at a time to the graph with all the corresponding edges to, you know, iteratively build larger and larger graph. So these models are usually easy to train. The downside is that you need to enforce an ordering of the graph, which, as I covered before, you know, doesn't necessarily exist, right? And because of this, these models tend to memorize the training data and are also often not very good at capturing global structure of the graph. Well, they do recreate local structure quite nicely. An alternative to this is one-shot approaches, you know, like mostly based on VAEs or alternative adversarial networks that aim to sample some noise, feed it through some potentially permutation equivariant neural network that gives you directly the adjacency matrix of a graph. So, you know, these models, if they use equivariant neural networks, have no dependence on the ordering, and, you know, they're parallelized, they're fast, but so far they only could successfully generate graphs of like 10 or 20 nodes, so very, very tiny nodes. Yes, in this work we will mainly focus on GAN approaches that fall in these one-shot paradigm. And as you all probably know, you know, in a GAN framework, you have some sort of a generator which samples some noise, feeds it to a neural network, in our case, an equivariant neural network that gives us some graph, right? And we have a discriminator graph neural network that tries to tell if these two graphs are same or not. So these approaches, as I just mentioned, do not really scale to larger graphs well. And one of the potential reasons why this is so is that if, let's say we want to generate a tree, like one on the right, we want to ensure that this tree graph, to be a valid tree, doesn't have any cycles, right? But for this, every node effectively needs to learn the global structure of the graph to ensure that, you know, when an edge is introduced, it doesn't create a cycle. And in these one-shot models, the interactions between different nodes or different points are usually pairwise. So you need like order n layers or interactions to capture the global structure of the graph, which, you know, as the graph size grows, becomes quite prohibitive. So the question is, you know, like, can we do better? How can we solve this? So in our work, we take inspiration from the spectral graph theory, and if we would take the population of the graph, you do this spectral decomposition and take the first couple of eigenvectors, we usually get quite nice clustering of the graph. So for example, here above, you see some samples of graphs, and below you see the clustering applied with first two eigenvectors of these graph populations. And as you can see, they nicely capture the global structure. And the idea that we had is that, you know, if we can first generate effectively this high-level clustering of a graph, then it's probably easy to fill in the local connections or local edges to create a full, nice graph that captures the global structure. So a bit of a spoiler alert, one can actually do this, and this works. So, you know, in our approach, if you take some generated graph, you know, here below, take its spectral embedding from first couple of eigenvectors above, you can feed it in our model, for example, this true spectral embedding to get a graph that's almost the same, not entirely, but, you know, very similar. It's kind of what we want. And, you know, on top of this, we're able to generate a new spectra, right? So kind of new eigenvectors that could correspond to eigenvectors of a graph from a given distribution, right? And then we can build a completely novel graph using these generated eigenvectors. So how we do it is we effectively have three GAN models stacked together. You know, one GAN model to generate eigenvalues of the graph population, you know, one to generate the eigenvectors, and one to then create the adjacency matrix from these spectral embeddings, you know, from this clustering that we saw above. And most of these architectures are quite straightforward, you know, like eigenvalues are just sequences. For adjacency generation, you can use the methods that have existed before. But what is quite special is how we generate the eigenvectors. So the eigenvectors, in this case U, denoted by U, are orthogonal unit length vectors, right? So for example, we take first k eigenvectors and, you know, put them as in this column matrix. We can transform one set of eigenvectors into another set if we multiply them by rotation matrices from left and from the right. You know, and then we want particularly such a refinement with rotation matrices to retain the eigenvector qualities of being orthogonal and a unit length. And in fact, just having this multiplication with a rotation matrix from the left already allows us to transform any sort of eigenvector matrix into any other eigenvector matrix. So this is kind of as expressive as it could be in that regard. And so in our model to generate eigenvectors, we effectively use this iterative refinement with multiplying with rotation matrices from the left and from the right. And for this, you know, we build an equivariant architecture that effectively just gives us these two matrices, and then, you know, in every layer we can build new left and right multiplication matrices based on the inputs to refine them, and build a final eigenvector matrix U that we will use for adjacency generation later. You know, and this matrix is just built, you know, from some initial fixed input that's then refined by this these rotations that are constructed using effective eigenvalues and some noise. So going to some results, like this approach, this two-level approach, this first generates clustering and then generates the graph, achieves much better statistical similarity to the ground truth graphs from the data sets on various synthetic tasks than competing approach, both other previous existing GAN approaches and also the state-of-the-art regressive methods. What's also quite nice is that in this case, our approach is the only one that can, for example, generate planar graphs that are planar, actually, and have not been seen in the training set, while all other methods fail at it. And also, as the approach is this one-shot, compared to these previously state-of-the-art ultra-regressive methods that had nodes to the graph one by one, our approach is orders of magnitude faster due to parallelization. And if we look at some actual generated samples, we can see that they look quite nice. For both planar graphs, stochastic block model graphs, we can also generate like large protein structures, well, non-attributed protein structures. So this is more of a toy task, even though it's on real-world data. Of course, these protein structures look still a bit for all of the models, but this is not a very realistic task, and there are better ways to generate attributed proteins in a similar way to our approach. And of course, we can also generate like for example attributed molecular graphs, again in a similar way. That was another way to apply the model. And thank you for your attention. And if you have any questions, feel free to reach out or look at our paper for more details, as this was quite a high-level overview.
Thank you, Karolis, and for this amazing presentation. Okay, so right now we going back to presentation. Yeah, so thank you thank you very much, Karolis, and amazing presentation. And this is our last nominee for this best research paper category. I want to really thank every nominee for incredible work. Also want to thank all the researchers from Lithuanian origins, like Karolis Baltrūnas, Gintarė Klibaite, for doing like incredible work and making huge contributions in AI world and also in Lithuanian AI community. So thank you everyone, and let's go to our next category. It's called AI Company of the Year. And we have 4 nominees in this category. So first one is a startup company called Expressivity. So this is the retail shop powered by AI. So if you in Vilnius and Pilies Street, there's a small shop. I think right now it's called Iki, with this black sign. So you can go there and try this autonomous shop without any cashiers, where you can like just put things, and before you go, you just pay with your card and that's it. So this is amazing product and very unique one in all Europe. So yeah, congratulations, Expressivity, amazing product and really worth for this be nominated for this category. Another company called Ovoko. So this is a Planet Positive marketplace for used car spare parts. So the company uses a lot of computer vision. One of the tasks for computer vision to check this serial code on different used parts. And this is quite like a hard task because most of these numbers don't really see that much. They have different structure and all these parts are different. One from plastic, from metal, and from other things. So yeah, so this is the incredible AI work what they are doing. They also using classification to classify what part it is, because they have like thousands of parts. So they create this like machine learning algorithm that could help them to identify products, and then computer vision, OCR, and other things to identify the serial number. And if you want to learn more, 2 months ago, we have meetup with senior data scientist of Owoko, Jonas. So we have our, if you want to check, we have this recording in our YouTube channel. So another company is Neurotechnology. So this company is probably the oldest AI company in Lithuania. They are more than 10 years and they have like different kind of applications. They are most popular for biometrics, but they also work into NLP, recognition technology. And what I see, like every year they release some new product. This is quite amazing. And yeah, they are worth to be in this list really too, as other companies. And the last company is Agnes. They are creators of EasyFlow. So EasyFlow is a video analytic platform that could help you analyze your video in real time and every video you have. So they also creating a lot of applications for AI for public sector. So if you want to check more for all these companies, we put links to their websites that you can read more and understand what they are doing. They also, some of these companies are hiring. So if you are AI engineer and want to work with these incredible technologies in Lithuania, so this is like very good chance for you. Okay, so another category, also very important, AI application award. And we have like 3 applications that are quite interesting and contributing a lot. So one of them is called Solitech, a smart electricity storage system. I'm really surprised that this company is a Lithuanian company and they're creating this incredible product, how to store your electricity smart. I think this company mostly working with solar panels. So this storage units are quite important for people to have in their homes, and the AI could help them to optimize all these processes. So this amazing application and the product. Another is by Communication Ministry, RRT, and Oxylab for a tool to detect malicious and uncensored content. So basically, they're checking the content on the internet and trying to detect for some malicious or uncensored content. And it's called Clean Internet or Švarus Internetas in Lithuania. The last, also quite important application is STEAM Center in Panevėžys, having these courses for children about AI. And I think this is quite important to educate children from the beginning and from the small age. What is AI and how to create AI, how to create these small applications, because we can boost our science field, have more researchers, but also these kids start living in the life where AI will be probably the main technology. All technologies will be based by AI. So just like this, yeah. Okay, and the last nominees category is called AI Publicity. So this is for all the work to showing about AI, talking about AI on the public channel. So first nominee is Technology Show Debatte. This is the podcast and I think radio show, if not, I'm not mistaken. And they are mostly every week talking about new technologies, how technologies will change, and they do quite a lot and talk quite a lot about AI in previous year. Another publicity event, or it's Ministry of Economics and Innovation and organization Kurk Lietuvai, Grateful Lithuania, for the project Dirbtinio intelekto proveržio skatinimas. So this project was based to have better knowledge how Lithuania become a better ecosystem for AI startups, companies, research centers, researchers, and in general how AI could help like current companies, current sectors to be like more productive and create more innovations. So this is quite incredible. I'm really glad that Lithuanian government doing these initiatives because AI is quite important, and this is how we can improve our economy and also create amazing innovations. And the last one is last nominees are organizers of International E-Conference on Artificial Intelligence and Human Rights. This conference was based mostly on the legal standards, how we should control AI and how we should pay more attention, what should be the human rights and all these important topics, which is, as we see more and more technologies released every week, and this is quite important to have like legal background and standards how to control these technologies, that they don't not become like malicious and things. Yeah, so the organizers are Infoflex, Michael Romero University, and newsletter and website for news Verslo žinios. So this is the all nominees, and I want you to remind one more time that next week on December 14, we have AI Awards. We still have a couple of seats left. All the awards ceremony will be held in Mo Museum. So I think one of the prettiest place in Vilnius. So we're glad that we have this venue space. And yeah, so if you want to register and meet other AI enthusiasts, specialists, people from industry, government, so this is the right event. And we only do these events probably once or twice per year. And this is AI Awards. This is like most bigger event we are doing. So we want to invite you to this event to talk with people. Also, always we have like after party after that, so we can like talk about ideas and new development in AI. So I really encourage you to register. So all the links are in this video descriptions. And if you have some kind of things that you want to show to us or have some ideas how you can help us to improve content or something like that, we're always looking for people. And if you have something that will be interesting to do, project or something like that, we also could help you with that. So this is our contacts. You can contact us website, lithuania.ai, email address, and Twitter. So thank you very much, and see you next week on AI Awards. So thank you very much. Bye. Have a nice day.